Hey everybody, so let's look at this factorizing algebraic expressions challenge worksheet that I've given out to some students. It's pretty tough. It's well beyond what you would consider 7th grade math. That's why it's a challenge. That's why it'll probably be worth a decent amount of extra credit if you do it. So even the way this is written, the way this is presented is more like what I remember seeing in college, like, my freshman year or something, intermediate algebra. So yeah, kind of higher level stuff, but I think that you guys will be able to figure it out. It's not that bad. So the first section, I believe, let me remind myself here. Yeah, so it's just about writing the expressions in factored form or factorization like we've been doing in class, but these are much more complicated examples, and they have variables being multiplied by each other. Like here you have a 3xy term. That's a little bit different than anything we've been handling in our normal stuff. And also here we have variables raised to different powers, like we have y squared here and x squared here, and that's a little different than what we've been doing. So we want to figure out what is the biggest factor that we can factor out of these three terms here. And we have to consider what's going on with all the different parts. We have to consider the numerical part of each term, so like the 3, the 9, and the 6, and the x's in each term. So this one has x to the first power, this one has x to the first power, and this one has x to the second power. And we have to consider what's going on with the y's in each term. So this one has y, this one has y to the second power, and this one has y. And we find all the things that are in common with each term, and we factor that out, and then we write the remaining terms as what would be left when we divide whatever it was that we decided to factor out. That probably sounded really confusing. So let's look at what this example says here. It looks like they're writing each one of these terms as a product with 3xy. See how the first term is the same as 3xy times 1, because it is 3xy? The second term, 9xy squared, that's the same as 3xy times 3y, because if you multiplied the 3's, you would get a 9, and if you multiplied the y's, you'd get y squared, which is what we had in that term to begin with. And then the third term, 3x squared y, well, that's the same as 3xy times 2x, because if you multiplied the 3 and the 2, you get the 6, and if you multiplied the 2 x's, you get an x squared. So what they're trying to show you here is that each term has a factor of 3xy in it. And so they factor that 3xy out here in this second line. And what remains is what that other factor of each term was, or in other terms, or in other words, what you would get from each term if you divided it by 3xy. If you divide 3xy by 3xy, well, you get this 1. If you divide 9x squared by 3xy, well, you get the 3 left over. You don't have any x's left because there was 1x in this term and you divided out 1x. But you have a singular y left because you had y squared in the original term and you divided out 1y. So it's just like the factorization we've practiced with much simpler expressions in class, but now you just have to look for not only numerical parts of a term that you can factor out, but what variables can you factor out as well. And all you have to do is look to make sure that that variable is in every single term. So like if I were looking at this one down here, example 1, I want to see, is there an a in every single term? This one has a squared, so good. This one has a squared. This one doesn't have any a's. This one has b's and a's. So I can't factor out an a from every single term because this one right here doesn't have any a's. And so what they did instead is they factored out a's from the first two terms and wrote them separately. So because both terms had an a squared factor, that allowed them to factor out this a squared. Whatever the lowest degree, that means how big is this exponent, the little number up here, whatever the lowest number that is in every single term that you're going to factor out, that's what you can factor out. What I mean by that is if you had 3x to the 1, 3x squared, and 3x to the 9th, and you wanted to factor out 3 and some x's, you could only factor out x to the first power because that's the lowest number of x's we see it here. You can't factor out x squared or x to the third or x to the fourth or x to the ninth because essentially you don't have that many factors of x in this term. The lowest degree, this number here, sort of determines or limits how much you could factor out. So I encourage you to look through these examples and kind of see what they're doing. And then I'll work a couple of these exercises for you. I also encourage you to maybe do different ones than you see me doing right now, rather than just copying me. Like I'll show you, let's do C. C looks pretty complicated and a little different. So I'll write the expression on the first page of the response sheet back here that says section 1. So wait, this is gonna be hard, I gotta memorize it real quick. It is 6xy plus 10x squared y. And so I look at the 6 and the 10, and I see that they share a factor of 2. So I'm going to factor out something with a 2 in it. And then I see that they both have x's in them. This is x to the first power. Like if there's no exponent over a variable, you can always just think of it as to the first power. This term has x to the first power. This term has x squared. The highest number of x factors that I can factor out is determined by the lowest exponent among all the x's. And so I have an x to the 1, so I can only pull out x to the 1. And then same thing with the y's. I have y to the first power and y to the first power, so I can only pull out y to the first power. And what's left is what happens when I divide these things out from each term. So when I divide the 6 by the 2, I'm left with a 3. When I divide x by x, I'm left with just a 1. And I'm not going to bother writing that 1 because these terms are factors, they're multiplication. So multiplying by 1 doesn't do anything. That's not worth writing. And same thing with y divided by y. I would just get 1. So what's left when you divide 6xy by 2xy is just a 3. And then when I divide the 10 by the 2, I get a 5. When I divide x squared by x, now remember x squared means x times x. And then when you divide that by x, well, this x divided by x, you could say they cancel out, or in other words, any number divided by itself equals 1. And so these two things right here make 1, and what you're left with is x times 1, or in other words, just x. So this x squared divided by that x is x. This y divided by this y is just a 1. And so this is a standard form expression. This is its factored form. Let's do another one. Let's see here. Oh, I'm lost in the pages here. Wrong section. Let's see here. I'll do D. Since that one has some higher degree exponents in it, it'll be interesting to see what happens there. So it's m to the 4th minus 3m squared. So m to the 4th power minus 3m squared. So now I see that the highest, sorry, I keep saying highest when I want to say lowest. The lowest degree of m out of all my terms is this 2. And so that means I can factor out an m squared of this one. I look at the numerical parts of these two terms. This one doesn't even have a numerical part. There's a 1 there, but we just don't write it. And this one has a 3. So I'm not going to factor out any numerical part of this. I'm just going to factor out m squared. M to the 4th divided by m squared, well, remember m to the 4th, that means m times m times m times m. And we divide that by m squared, that's m times m. Well, each m that we're multiplying by on top, if you pair it up with an m that's dividing on the bottom, well, it's being multiplied, but its action of on those on the top is division. We could essentially pair them up. This m and this m divided by m, they make a 1. That's what people mean when they say they cancel out. This m and this m they also make a 1. Like think of it as a fraction m over m, right? Any number over itself is just 1. So that's what I mean by when I say these are making 1s. And we're left with 2m still on the top. And so that means we have m squared. We didn't have to go through all that though. You could have just subtracted the exponents. I had m to the 4th to start with, and I was dividing it by m to the 2nd. Well, 4 minus 2 could have got me that too. So you could always just subtract the exponents when you're dividing different degree variables from each other. So here, I still have my 3. M squared divided by m squared is just a 1, so I have nothing. Well, I have a 1. I shouldn't say nothing. All right, let me do one of these other ones where they want you to do 2 factorizations in one expression. They want you to factor the first part and the second part. I keep turning to the wrong page. All right, so here it says factorize the first pair, so like the first 2 terms, and then factorize the second pair. So you're going to wind up writing 2 different sums within parentheses with some factor multiplying on the outside. How about I just jump straight to the last one because it's probably the most challenging if I had to guess, and then I'll let you handle the rest from there. So it says 6y squared minus 15y? Yeah, 6y squared minus 15y. 6y squared minus 15y and plus 4y minus 10. Plus 4y minus 10. And so I see common factors of y and 3, because 3 goes into 6 and 15 from the first pair. And then I don't have common factors of y in the second pair, because this one doesn't have a y. But I have a common factor of 2, because 2 goes into 4 and 2 goes into 10. So I think I'm going to factor out a 3y from the first pair. And what's left here is 6 divided by 3 is 2. Y squared divided by y is just 1y. And then 15, let me put my minus sign. 15 divided by 3 is 5. Y divided by y is just a 1, so I won't write anything. Then I need my plus sign. And I'm going to factor out a 2. So what's left is, well, 4y divided by 2 is 2y. And 10 divided by 2 is 5. So I factored something out of the first pair, and I factored something out of the second pair to write a new factored form expression. All right, let's try some of the expansion ones. These are actually a little bit harder and a little bit more interesting. Probably shouldn't even talk that long about the factoring ones. You probably could have figured it out without me talking that much. All right, so let's look at this first example. This is called a difference of squares. This right here. People refer to this as a difference of squares or the difference of squares. The reason they call it that is because I'm going to write it a little bit bigger in case you're having a hard time seeing it. The first thing is a squared number, x squared. The second thing is a squared number, 3 squared. And you're taking their difference. That's what it means when you subtract things. So people call this a difference of squares. And what's super nice about difference of squares is they have a really easy way of factoring that always works. I'm sort of showing you this example backwards. They started with this x plus 3 quantity times x minus 3 quantity and wanted to show you that that would come out to a difference of squares. I actually like to look at it the other way. I like to look at the fact that if you have a difference of squares, then you can always write that as the square root of the first thing, which the square root of x squared is just x, the square root of the second thing, which in this case, since we're already writing it as 3 squared, we know the square root is 3, right? Because 3 squared is equal to 9, and its square root is 3. So that's the convenience of writing it this way. Plus 3 times quantity x minus 3, right? If you can write an expression as something squared minus another thing squared, then you can always factor it as the first thing, not squared, plus the second thing, not squared, times the first thing, not squared, minus the second thing, not squared. And the reason that works is all in the math here. Okay, I'm not going to go through and explain it. You can sort of watch how they've done the distribution here and see why it works. And so this is them just sort of more explaining the rule here with like a squared minus b squared. They changed it to x and 3. I'm not sure why. This is the general rule. This is the thing that matters the most. This is the thing you would see in a college textbook. This is the thing you'll probably use a lot in your life. A squared minus b squared is the same as a plus b times a minus b. And that's the rule that you got to kind of practice in some of the exercises here in the back. Then there's this other thing called the perfect square, right? That's when instead of it being some value squared minus some other value squared, you have two things in a sum, and you want to square that sum. So notice that the exponent is outside the parentheses here. And so what this means is it doesn't mean x squared plus a squared. That's the biggest mistake that people always make. This is not this. No. What it actually means is you have to take the sum x plus a and multiply it by its own self, the sum x plus a. And there's the way I learned to do this is this thing called FOIL. And it stands for, can you see way down here? Nope, so I'm going to write up here. FOIL stands for first, outer, inner, last. And I'll show you where each one of these positions that I mean that we're going to multiply is the first. So when you're looking at two sums or differences in parentheses like that, when I say the first terms, I mean these two here, here and here. When I say the outer ones, I mean here and here. So first means the first two terms in each one. Outer means the first over here and the last over here. Inner, those are the ones closest to the middle. So here and here. And then last, well, that's the last one in each parentheses. So here and here. And so if you multiply the two first terms and then write what you get from there, and then multiply the two outer terms and write what you get from that, and then multiply the two inner terms, write what you get from that, and then multiply the two last terms and write what you get from that. That's how you expand through distribution when you have two things in parentheses right up against each other. So here's their example. We're trying to do x minus a times x minus a. This middle line, or this second line, would be a little confusing if you were trying to listen to my explanation, because they're doing it a slightly different way. It's not wrong, just if I were teaching it slightly different, I would show you this way. Instead, I want you to look at the next line. This x squared came from them multiplying the two first terms. Then this minus ax came from them doing the two outer terms. Right? Because they have x times negative a, so negative ax. And then the next minus ax came from them multiplying the inner terms. Right? Another minus a times x, so minus ax. And then that last thing, that a squared, well, that came from them doing the two last terms in each one. The negative a and the negative a gave a positive a squared. So they essentially foiled right here. And so if you get really good at that, then you can do a lot of the stuff in the exercises here. So let me show you. I don't need to do the response sheet. I can just work right here. I got a bunch of different colors here. I'll use red. So if I wanted to expand these two sums, or I guess this one's a sum, this one's a difference, however you want to think of it, in the parentheses here, I just FOIL them. I'm going to do first, so that's x and x. I get x squared. And then I'm going to outer. That's the x and the negative 2, so I get negative 2x. And then I'm going to inner, and that's this 2 and this x, and they're both positive, so I get plus 2x. And then I'm going to last, which is this 2 and that minus 2. So that's, well, 2 times 2 is 4, but it's negative because there's a negative in there. And now look what happens. I have a negative 2x and a positive 2x. When you add them, you get 0. And what's left is just the x squared minus 4. But we already knew that was going to happen if you were paying attention, because this is a difference of squares. Right? X squared, that's x times x, that's x squared, obviously. And then 4, well, that's 2 squared. And so it was written as x plus 2, x minus 2. So, you know, when you get really good at this, you would never have to actually do all this foiling. You would look at, oh, x plus 2, x minus 2. Oh, well, then I know that has to be x squared minus 2 squared, because you're used to seeing these differences of squares. All right, and so all of these in here, like not all of these will come out to a really nice difference of squares like this. The first 4 do. No, actually, no. Looking through, no, they all do. All of them will do this. So if you get good at this trick, you can do some of these pretty easily. So these are all difference of squares, all up in here. You just got to think of what happens when you square each thing and then write it properly. And then these are also differences of squares here. But instead, they've given you this form here, and they're asking you to factorize it, where here they've given you the factored form and they want you to expand it. These, on the other hand, over here are perfect squares, right? This is where you're doing x plus 5 times x plus 5. That's the same as this, if it was written as x plus 5 quantity squared. And these you got to FOIL. These, unless you remember the rule, they actually come out the same way every single time, and the rule is on the previous page. I'm not going to go through it. You can see, if maybe doing a couple of them, you'll kind of figure out the rule, or you can go back and look at the examples from the previous page and sort of get the rule. But if you don't get the rule or you can't figure it out, you can always just FOIL these. First, outer, inner, last. I feel like I should do one of these for you before I turn this video off. So let's see here. How about E? 2m plus 5 times 2m plus 5. So I'm going to first, so that's the 2m times the 2m. That's 4m squared. And then I'll outer, that's 2m times 5, which is 10m. And then I'll inner, that's 5 times 2m, so that's another 10m. And then last, 5 times 5, which is 25. Notice how I got 2 of the same thing in the middle, the 2 10m's? That's part of the trick that always happens. I'm not going to explain it much more than that, but I think you'll see that happen a lot. All right, good luck.